Welcome viewers to the second segment of the fifth lecture for the online series of lectures for the course of Algebraic Topology 2. We begin this segment with a few applications of exact homology sequences. Application of exact homology sequences. So I want you to prove the following result. Prove the following result known as the Steenrod 5 lemma. Which involves 5 homomorphisms between abelian groups. Steenrod 5 lemma using the diagram chasing technique that you learned in the previous lecture. Diagram chasing technique. Okay, so let me state this result. I'm not going to prove it, it's left as an exercise. Lemma 1, the Steenrod 5 lemma, it's a useful one. We'll see its use in this lecture. Suppose one is given the following commutative diagram. Of abelian groups and group homomorphisms. A1 to A2, A2 to A3, A3 to A4, and A4 to A5. Okay, there are group homomorphisms connecting these groups, abelian groups, and there is from B1 to B2, B2 to B3, B3 to B4, and from B4 to B5. Okay, and F1 is a group homomorphism from A1 to B1. F2 is a group homomorphism from A2 to B2. F3 is a group homomorphism from A3 to B3, and F4 is a homomorphism from A4 to B4, and F5 is a group homomorphism from A5 to B5. We are given that this diagram commutes, where the horizontal, in addition to the commutativity of the diagram, we are also given the fact that the two horizontal sequences are exact. These two sequences are exact, where the horizontal sequences are exact. Now, if F1, F2, F4, and F5 are isomorphisms, okay, we are given that they are group homomorphisms, so they are given to be bijective group homomorphisms. Okay, if these four group homomorphisms are bijective, so is F3, this one. F3 is also an isomorphism. one has to prove. Okay, so this I leave as an exercise. Okay, okay. Now let me get to the second lemma of this lecture. Lemma 2, which I am going to prove. Let H from the pair k comma k0 to the pair L comma L0 be a simplicial map. Okay, simplicial map. Recall from the previous lectures that a simplicial map between two pairs. Here K0 is a subcomplex of K and L0 is a subcomplex of L, and the map between these two pairs is called a simplicial map if H from K to L is a simplicial map that takes each simplex of K0 to a simplex of L0. Right? So let me write it for you. H from, so I'm writing the definition, I'm reviewing the definition of a simplicial map between two pairs. H from K to L is a simplicial map which takes each simplex of the subcomplex K0 to a simplex of the subcomplex L0 of the complex L. Okay, so this is the definition of a simplicial map between two pairs K comma K0 and L comma L0, where K0 is a subcomplex of K and L0 is a subcomplex of L. Okay, then the following results hold. The induced homology homomorphisms, the induced homology homomorphisms H star at P from HP K comma K0 is a relative homology group. The pth relative homology group of K mod K0 to the pth relative homology group of L mod L0. Give a homomorphism of the exact homology sequence of the exact homology sequence of the pair K comma K0 with that of L comma L0. We learned earlier in earlier lectures that we learned the definition of homomorphism between two sequences. Okay, so here part A tells us that there is a homomorphism between the exact homology sequences of the pair K comma K0 with the pair with the one of the pair L comma L0. Okay, so there are two exact homology sequences, one for the pair k comma k0 and another one for L comma L0. And these two exact homology sequences talk to each other by means of a homomorphism that is induced um, from the simplicial map H. Okay. Now part B tells us that if H star H tilde star I from hi of k to hi of L and H tilde star 0 I from hi of k0 to hi of L0 are isomorphisms for I equal to p and p minus 1, then H star at p from the pth relative homology group of k mod k0 to the pth relative homology group of L mod L0 is an isomorphism as well. To prove this, we are going to use Steenrod 5 lemma. Okay. Now, C tells us that both these results, both A and B, hold if absolute homology, these homologies, okay, these homology, these relative homologies as well. If absolute homology is replaced throughout by reduced homology. Okay. Good. Now I'm going to prove lemma 2. Let me erase everything. We'll get started with part A. Proof of part A of lemma 2. Recall from lecture 4 that the simplicial map H, which is a simplicial map from the pair k comma k0 to L comma L0, induces at the chain level, induces a homomorphism, group homomorphism at the chain level, H hash at P, which is a group homomorphism from the chain group CP k comma k0, relative chain. The group of relative p chains of k mod k0 to the group of relative p chains of L mod L0. Let me take a look if this is the correct term that I'm using for relative homology groups. I have a very bad habit of forgetting things. I hope I'm using the correct term. I have this reduced homology thing. Relative homology. Yes. Um, Relative chains of K mod K0. Yeah. So it's the pth uh, relative chain group of K mod K0. Right. There is an induced homomorphism at the chain level. Okay, we know it from the fourth lecture. One similarly, so one similarly obtains the following induced maps at the level of chains. Okay, um, this induced homomorphism is at the level of relative chain groups. Okay, now for the absolute chain groups, we have the induced homomorphism as well, which we denote by H tilde hash at P, which is a group homomorphism from Cp of K, the pth chain group of K to the pth chain group of L. And then we have H tilde 0 hash at P, um, which is the homomorphism from the pth chain group of K0 to the pth chain group of L0. Okay, so we have these three induced group homomorphisms. Okay, as a matter of fact, there are the following exact sequences of chain complexes. The following exact sequences of chain complexes that we know from our knowledge of lecture 4. 0 to is the trivial um, chain complex, 0 to the chain complex calligraphic C of K0 to the same chain complex C of K, and from C of K to C, the chain complex for the pair, and then back to the trivial chain complex. Okay, so this chain map from C of K0 to C of K is induced from the inclusion of K0 into K, which we denote by I hash K. The K stands for the fact that we are dealing with the complex K, right? So we'll have a superscript L when we'll be dealing with the complex L, right? So we are considering the chain complex of chain groups arising from the simplicial complex K. All right, that's why we are attaching that label K to the induced chain map from the inclusion of the subcomplex K0 into the complex simplicial complex K. All right, so now um, there is this chain complex C of K, okay, which comprises of the abelian groups of Cp of K, which are a pH chain group on the simplicial complex K, and the boundary homomorphism del pk. All right. So now there is a natural projection um, CP of K uh, projected onto the quotient group CP of K comma K0, right? Which is, this is the projection map, pi P, right? And this is the quotient group when we obtain by quotienting CP of K by CP of K0, right? And this is the induced chain map by hash, okay? And K again reminds us the fact that it's a chain map attached to the complex K, okay? So we have this, oh, sorry, I think I made a mistake here. It has to be here by uh, hash K, right? So this is an exact sequence of chain complexes. Similarly, associated with the simplicial complex L, we can write down a short exact sequence of chain complexes, which is 0 to, from the trivial chain complex 0 to the chain complex C of L0 to the chain complex C of L to the chain complex C um, L comma L0 and back to the trivial chain complex 0. And here we denote the induced chain map um, for the associated with the simplicial complex L. And here as well by hash L. Okay, these are two exact sequences of chain complexes where the a few words about the notations where the chain complex C of K, for example, is given by the family C of K is equivalent to this family CP of K, which are the pth chain group on the simplicial complex K, and equipped with the boundary homomorphisms del P K. Now we have the following. So, and besides, these guys are, chain maps, right? Well, H hash, H tilde hash, and H tilde 0 hash are all chain maps, right? And therefore we have the following commutative diagram. So let me draw this commutative diagram. I'm going to keep it intact. I will need it. Let me draw it on the far right, so that I don't have to erase it. 0 to CP of K0. The following diagram commutes for all P. Okay. CP of K0, and then from CP of K0 to CP of K, and here is the inclusion map. So it's the chain map induced by the inclusion map of K0 into K, and P determines the dimension, and then from CP of K to CP of K comma K0, the pth relative homology group of K mod K0, and then back to the trivial group. Okay. Now this is by hash K at P. Okay, in dimension P. Now at the bottom there is an exact sequence of abelian groups, which is 0 to CP L0 and then CP L0 to CP of L. Now this is I hash at P. I hash L, the superscript L designates that we are dealing with the chain groups related to the simplicial complex L. And then from CP of L to CP of L comma L0, and then CP of L comma L0 to the trivial group 0. And here this group homomorphism is by hash K, sorry, L at P. Okay, so these are two short exact sequence of abelian groups connected with group homomorphisms, and there are this group homomorphisms H tilde 0 hash at P. This is H tilde hash at P, and finally this guy is H hash at P. Okay, this is the commutative diagram. We all know. All right. Now, each of these maps, each of the maps, H tilde 0 hash, which is a map, which is a chain map from C of K0 to C of L0. These are two chain complexes, C of K0 and C of L0. And H tilde 0 hash is a chain map. Similarly, H tilde hash is a map, is a chain map from C of K to C of L. And H hash is a chain map from C of K comma K0 to C of L comma L0. Okay, these are three chain maps. Each of these maps is a chain map between the respective chain complexes. Okay, these are all chain complexes, and these three maps are chain maps. One can easily check that H hash at P H hash at P is a group homomorphism between the relative homology, relative chain groups, not homology, relative chain groups. This is from CP of K comma K0 to CP of L comma L0. This is a map between two quotient groups. Okay, the left hand side is the quotient of CP of K by CP of K0, and the right hand side is the quotient group of CP of L by CP of L0. Okay, so this is a group homomorphism, and this homomorphism commutes with relative boundary operators. with the relative boundary operator. Uh, it can be checked easily. Operator, okay, by commutation, by the fact that this group homomorphism commutes with the relative boundary operator, I mean that the following diagram commutes. So let me draw this diagram. This is a square Cp of k0, Cp of k comma k0, which is the relative p chain group of k mod k0 to relative chain group, a pth relative chain group of L mod L0. This is H hash at p. And then there is this boundary operator, which is del p k comma k0 relative boundary operator that takes us to Cp minus 1 k comma k0, which is the p minus 1 chain group of k mod k0. And then this relative boundary operator del p l comma l0 takes us to the p minus 1 chain group of L mod L0. And then I have this um, chain map H hash at p minus 1. This guy commutes. It can be checked that this guy commutes. That is del p l comma l0 composed with H hash at p is equal to H hash at p minus 1 composed with del p k comma k0. Okay, good. Now this equality holds. Hence, using our old knowledge from lecture 4, there is an induced since this guy, this group homomorphism commutes with the relative boundary operator, there is an induced homomorphism H star P at the level of homology. So this is going to be a group homomorphism between these two relative homology groups, pth relative homology of K mod K0 to the pth relative homology group of L mod L0. Okay. So there are other induced homomorphisms at the level of absolute homology groups. Let me write them out. There are other induced homomorphisms H tilde star at P, which is a group homomorphism from the group HP of K to HP of L, and H tilde 0 star at P from HP of K0 to HP of L0. Okay, so now we know that these induced group homomorphisms at the level of homology groups exist from our knowledge of lecture 4. Okay, let me erase everything here. Now, by means of theorem 4, or lemma 3, okay, zigzag lemma, or the exact homology sequence of pair, which was the title of theorem 4. Since this is a short exact sequence of chain complexes, this is the C of K0 is a chain complex related to the subcomplex K0, and there is this C of K and then to C of K comma K0, and then back to the trivial chain complex, and this is the chain map induced by the inclusion map associated with the simplicial complex K, and this is the chain map by hash K induced from the projection map. Since this is an exact sequence of cell complexes, there is a long exact homology sequence, right, by means of theorem 4 or the zigzag lemma, which we write as, so we get to HP of K0 and then to HP of K. So we consider the zigzag lemma in terms of the pair K0, K comma K0, okay. So we take a special case of the zigzag lemma when we prove theorem 4 of lecture 4, right? So take that special case corresponding to the pair K comma K0, and then we have this long exact sequence, long exact homology sequence. So this group homomorphism is I star K at P, and this is going to be pi K star at P, and this is the relative homology group of K mod K0, and then via this homology boundary homomorphism del star K. Here this superscript K means that we are working in the complex K. Nothing special about this superscript, it's just a notation at P. This is the homology boundary homomorphism, and that takes us to HP minus 1 K0 and goes on like this. This is a long exact homology sequence, okay. All right, this is we denote this long exact homology sequence by equation number 6. Now similarly, since 0 to at the, so for the simplicial complex L, we have a similar exact sequence of cell complexes, which is 0 to C of L0, and then from C of L0 to C of L, and then from C of L to C of L comma L0, and then back to the trivial cell complex 0, and the chain map induced from the inclusion map is I hash superscript L, since we are dealing with the simplicial complex L, and then this is induced from the projection map, and this is by hash L. Okay, since this guy is also an exact sequence of cell complexes, there is a long exact homology sequence, long exact homology sequence. So we write the analogous equation of 6 in the context of this simplicial complex L. HP of L0 to HP of L to H, the relative homology group of L mod L0, and then to HP minus 1 L0, and goes on like that. This is also a long exact homology sequence, and the group homomorphism from HP of L0 to HP of L is I star L at P, and the group homomorphism here is pi star L at P, and this is nothing but delta star L at P, this homology boundary homomorphism. Okay, so we denote this guy by this long exact homology sequence by 7. Okay, the two long exact sequences given by 6 and 7 talk to each other by means of a family of homomorphisms, right? And this family is nothing but, on the left we have a sequence of homomorphisms, and then we come to H tilde 0 star at P, then H tilde star at P, H star at P. We know what these homomorphisms are, right? Then back to again here, H tilde 0 star at P minus 1, and goes on like this on the right as well. Okay, so let me write down this these two exact long exact homology sequences talking to each other by means of this family of homomorphisms. Okay. Which is here HP of K0. This is the first homology sequence, a long exact homology sequence given by 6, I star K at P, then HP of K, then the Pth relative homology group HP of K comma K0, which means the Pth relative homology group of K mod K0 by K star at P, and then from it to HP minus 1 K0 by means of this homology boundary homomorphism del star K at P This is one exact homology, long exact homology sequence. One long exact homology sequence. There is another here at the bottom, which is HPL0 to HPL to HPL comma L0 to HP minus 1 L0 and goes on to the right like this. This is I star L at P. This is pi L star at P. This is del star L at P. Okay, and this group, this is a homomorphism, which is nothing but H tilde 0 star at P. We discussed it a while ago. This is H tilde star at P. This is H star at P. This is the group homomorphism of two relative homology groups, and this is again back here H tilde 0, but in the dimension P minus 1 now. Okay, so we have two long exact homology sequences, one corresponding to the complex K and the other corresponding to the simplicial complex L. Okay, and these two long exact homology sequences talk to each other by means of this family of group homomorphisms. Okay, this is what we are supposed to prove for part A. Now, the commutativity of these diagrams, this diagram, I mean the commutativity of all these squares involved in this diagram follow from this. Okay, we remember this. So this is the commutative diagram at the chain level, right? So the commutativity of this diagram at the homology level follows from the commutativity of the diagram at the chain level in the following way. So from the commutativity of this diagram, we see that H star hash at P composed with I hash K at P is equal to I hash L at P composed with H tilde 0 hash at P. Okay, so which square is this? I think this square, right? So we are talking about this square, H hash at P composed with I hash K at P is equal to equal to I hash L at P composed with H tilde 0 hash at P, right? This is the commutativity of this square. And well, from this one has, at the level of homology groups, H tilde hash at P composed with this is the induced homomorphism at the level of homology groups corresponding to this composed um, you know these composed homomorphisms. at the chain level. And similarly, we have to take the star of this guy, the induced homomorphism of this composite map, which is going to be I star L at P composed with H tilde 0 hash at P, the induced group homomorphism at the level of homology groups corresponding to this composite map. And we know that this is nothing but H tilde hash. Sorry, I have to get rid of this hash now. I am at the level of homology group, so it's going to be H tilde star at P composed with I k star at P is equal to I L star at P composed with H tilde 0 star at P. So this guy is the homomorphism, group homomorphism induced by H tilde hash at P. Okay, good. So, well, it means that this um, this composed with that is equal to this composed with this, right? Which means that it gives us the commutativity of this square. So commutativity of this square gives us the commutativity of this square. Similarly, commutativity of this square will give us the commutativity of this square, and so on and so forth. Okay, all right. So this was part A. Okay, now at this stage I need to review a few facts from from uh, the from the discussion on generic chain complexes and chain maps. Okay, let me do it. Let me erase everything. So we have been able to prove part A. Now, so I'll get back to the proof of I'm trying to prove lemma 2, right? I'll get back to the proof of uh, uh, part B of lemma 2, okay, in a while. But before that, I want to review a few things, right? At this stage, I want you to have a look at you to have a look at section 13 of the textbook by Moncrief, of the textbook, the book that we are following, Elements of Algebraic Topology, textbook by Moncrief. Okay, so let me help you with that. A chain map phi from the chain complex C to C prime. There are two chain complexes, C and C prime, and we have a chain map between them. This guy induces a group homomorphism So a while ago we applied this idea to prove part A. Okay, to prove part A of lemma 2, right? So we proved the commutativity of the diagram. which connects two long exact homology sequences corresponding to two simplicial complexes K and L. Okay, and we prove the commutativity of the diagram by using this fact, the fact that I'm writing now. Okay, so whenever I have a chain map phi between two chain complexes C and C prime, this chain map induces a group homomorphism from HP of C to HP of C prime at the level of homology. Okay, so in the present case, suppose we have this chain map H hash between these two chain complexes C K comma K0, the chain complex corresponding to the pair K comma K0 to the chain complex corresponding to the pair L comma L0. Okay, this is a chain map, is a chain map, and H star at P, according to the notation that we have been using. This is the induced group homomorphism at the level of homology groups. So this is the group homomorphism from HP of C. So according to this notation, it's going to be HP of C of K comma K0, which we denote simply by, for notational clarity, we denote it by HP of K comma K0. Okay, it's the pth relative homology group of K mod K0 to HP of C L comma L0, which we simply denote by HP of L comma L0, which is the relative pth homology group of L mod L0. Okay, these are for different p's. Okay, are the induced homomorphisms. Are the induced homomorphisms. Okay, so we have a chain map. As whenever we have a chain map between two chain complexes, we can translate to the level of homology groups. We can get group homomorphisms between homology groups. We can always do that, which are induced homomorphisms at the level of homology groups from the chain map between chain complexes. Okay, so this was one thing. We applied this thing while proving part A of lemma 2. Now also recall from section 13 that a chain complex calligraphic C is a family CP del P of abelian groups. These are abelian groups. And we have this family of group homomorphisms del P from CP to the group CP minus 1. Okay, there is a whole hierarchy of abelian groups here, and these group homomorphisms take us from one member, one abelian group to another abelian group in this family. Okay, indexed with integers, indexed, these p's are take value, they take value, P takes value in the set of integers indexed with integers such that del P composed with del P plus 1 is equal to 0. Okay. For all P. Now, if Cp is equal to 0 for all P, or for all negative P, then C is said to be a non-negative chain complex. Then C is said to be a non-negative chain complex. Okay. Now, so we want these CPs to be abelian groups. But if in addition it's a free abelian group, if CP is free abelian for each P, then this chain complex C is called a free chain complex. A free chain complex. Okay. In general, these abelian groups need not be free. Okay, but if these abelian groups are also free, then we call the underlying chain complex a free chain complex. The group, the quotient group HP of C that one obtains from quotienting out the kernel of the map, the boundary homomorphism del P by its subgroup image of del P plus 1. Okay, so one defines this guy as the pth homology group of the chain complex C. Okay, this is called the pth homology group, pth homology group of the chain complex C. Okay, now consider a non-negative chain complex. Okay, so let me erase everything. Concentrate on non-negative chain complex. If C is non-negative, chain complex, and augmentation okay, so it ends at 0. So for P negative, CPs are all taken to be 0. In that case, we are augmenting it, we are adjoining something to it to have things at the level of -1. Okay, so if C is a non-negative chain complex and an augmentation for C is an epimorphism. Okay, first of all, there has to be an epimorphism denoted by epsilon, which is a map from the 0th chain group, okay, which is C0, to the additive group of integers such that delta 1 so such that epsilon composed with delta 1 is equal to 0. So let me help you with this by drawing this diagram. So we come to C1, and then from C1 to C0 via the boundary homomorphism delta 1, and then from C0 to Z via this epimorphism epsilon. And we want epsilon composed with delta 1 to be 0, which means that we want the image of delta 1 to be in kernel of epsilon, which means we want image of delta 1 to be contained in kernel of epsilon. Okay, so the augmented chain complex, so we are given this non-negative chain complex, and we add this epimorphism to it, so that this is fulfilled. Then we have this notion of augmented chain complex. The augmented chain complex, which is a pair, this calligraphic C is the non-negative chain complex that we started with, and epsilon is the epimorphism that we are defining as the map from the group C0 to the group of integers. Is this augmented chain complex is the chain complex obtained from the non-negative chain complex C by adjoining the group Z in dimension -1. Okay, and using, so this is happening in the dimension -1, and using the augmentation map epsilon as the boundary operator, in dimension 0. So this is the boundary operator here. Okay, the homology groups of the augmented chain complex, the homology groups of the augmented chain complex C epsilon are called the reduced homology groups, of the original chain complex. Calligraphic C relative to the augmentation epsilon. Relative to the augmentation epsilon. Okay, so we have this augmented chain complex. So the homology groups of this augmented chain complex is the same as the reduced homology groups of the original chain complex calligraphic C, which was taken to be a non-negative chain complex. Okay, so these homology groups are denoted by either the homology, the ith homology group of the augmented chain complex calligraphic C comma epsilon, or by reduced homology of the original chain complex. Okay. Now we have certain results in the light of what we did before. The reduced homology, the pth reduced homology group of the non-negative chain complex C is equal to the absolute homology group of the non-negative chain complex C whenever P is not equal to 0. Okay. And when P is equal to 0, one has H0, the zeroth absolute homology group of the non-negative chain complex C is equal to the reduced homology group, of the non-negative chain complex C in dimension 0 direct sum, the additive group of integers. Okay, so together we have equation number 8. Now, so there is another point about chain maps, which refers to composition of chain maps. If phi is a chain map from the chain complex C to the chain complex C prime, and psi is another chain map from the chain complex C prime to the chain complex C double prime, then psi composed with phi is a chain map as well. And the induced homomorphism of the chain map of the composite chain map, this one, of the chain map psi composed with phi, which is a chain map from the chain complex C to the chain complex C double prime, reads the induced homomorphism is equal to psi star composed with phi star. This is what we used to prove part A of lemma 2. Okay, or if we restrict ourselves to dimension P, then psi P composed with phi P star is equal to psi star P composed with phi star P. Okay. So this is precisely what we used while proving the commutativity diagram, the commutativity of the diagram, where we had these two long exact homology sequence connected by families of homomorphisms. Okay, good. Now, if C comma epsilon is an augmented chain complex and C prime comma epsilon prime is another augmented chain complex. So if these are augmented chain complexes, the chain map phi from the chain complex C to the chain complex C prime is said to be augmentation preserving if epsilon prime composed with phi 0 is equal to epsilon. Okay, so in other words, we have the following commutative diagram. So let me draw this commutative diagram. This is C1, okay. So the chain group in dimension 1, and then we have the chain group in dimension 0. It's related to the chain complex C, and then the augmentation map epsilon from C0 to Z. And now let us go to the chain complex C prime, or the augmented chain complex C prime comma epsilon prime, where we have this exact sequence. This is the chain group in dimension 1, C prime 1, and this is the chain group in dimension 0, C prime 0, and then one has this augmentation map epsilon prime, which takes C prime 0 to Z. Okay, and there is a chain map, right? Phi. So this is phi of phi 1, and this is phi 0, and we take this to be the identity map, which is nothing but phi minus 1. Okay, it's the homomorphism, is the group homomorphism in dimension -1, because the groups in dimension 1 are just the additive group of integers Z. Okay, and the group homomorphism between them is taken to be the identity map. Okay, so the commutativity of this diagram, the rightmost square, gives us that epsilon prime composed with phi 0 is equal to epsilon composed with the identity map. Right? Identity map composed with epsilon, which is just epsilon. Identity composed with epsilon, which is just epsilon. So commutativity of the last square gives us this one. Okay, so in other words, we want this diagram to commute. So this is what we mean by a chain map between two augmented chain complexes. This is one augmented chain complex, this is another augmented chain complex, and whenever we have a chain map between two augmented chain complexes, we have to have this diagram to be commutative. Okay, in this case, phi is called a chain map of augmented chain complexes. Okay. So this is the notion of a chain map between augmented chain complexes. Okay. Now it follows that whenever we have a chain map between augmented chain complexes, this chain map preserves the this chain map preserves the augmentation, right? And this map in turn induces a group homomorphism, which we call phi star, which we denote by phi star p, which is a map between the respective reduced homology groups, or the absolute homology groups of the augmented chain complexes. Homology groups. So this is the induced homomorphism between the reduced homology groups, as long as phi preserves augmentation, or phi is a chain map between the augmented chain complexes C comma epsilon to C prime comma epsilon prime. Okay, good. So at this stage, I'll take a break, and using the notions that we have discussed just now, we'll be proving part B of lemma 2. Thank you for attending this second segment of the fifth lecture.